Yeah, so first, yeah, it's a pleasure to have Kobe virtually. Kobe Sonnenschein is going to tell us about holographic inspired stringy hadron. So thank you, Kobe.
Thank you very much for the invitation to come and present this seminar. So I'll tell you about a model that I've been working on in the last few years, mainly with my former student, Doreen Weissman, who is currently a postdoc in Japan. So the title is the Holographic Inspired Stringy Hadron Model, and I'll try to be as broad as possible. I'll describe some details about the spectra that this model provides, and about decay processes, which is less discussed by other models. Then I'll come to this topic, which is in fashion recently, and that is exotic hadrons, like tetraquarks and so on. And then finally, I'll talk about how to go from stringy scattering amplitudes to protonic ones. So the idea is to construct a phenomenological unitary string model, and I want to emphasize it's a model, it's not a theory, that is in accordance with as much as possible experimental data on hadron physics, and to be able also to do some predictions. The model, unlike what we usually do in holography, is in 4 flat dimensions, and but it is inspired by strings in a curved higher dimensional background. Okay, and eventually, of course, the challenge, which we are very far from yet, is to relate it to QCD. Okay, so the construction of the HISH model is based on several steps. I'll describe them step by step, and please ask me questions at any moment. So the first step is to determine a prototype or prototypes confining holographic backgrounds, and I'll define it in a moment, and to which we add the flavor brains. Then the second step is to analyze classical string configuration in these confining holographic backgrounds that correspond to mesons, baryons, globules, etc. Then, and that's the main point, is to map these systems of classical strings into classical strings in flat 4 dimensions, and with NC equal to 3 that relates to the baryons. Okay, and of course I want to emphasize that that's some kind of a map that's set by hand. It's not some controlled approximation. Then once we are done with the classical configuration, we want to quantize the system. Quantizing it in the holographic curved background with Ramon field is not something that we can do, but on the other hand, in this other side, in the 4-dimensional flat space-time, even though the theory is not free anymore, it's in an interacting theory, as I'll show you, but still we can, in certain approximations, we can quantize it, fully quantize it, and then extract. Well, the point is that it will be associated. It will be associated with adding some non-trivial boundary conditions to the strings, which come in the form of endpoint particles that carry masses, charges, spins, and sometimes baryonic vertices. Well, once we set up the quantum fluctuations around the classical solution, we need to renormalize the string theory, and renormalization cannot be done in the usual way of using the zeta function renormalization, but we use a different method, which is, if I use again the word inspired, it's inspired by the Casimir effect. So I'll describe how we do the renormalization. And of course, since we are doing, we're describing theory in 4 flat dimensions, non-critical dimensions, and we have to incorporate also the Liouville mode. Okay, then once we have this quantized system, then we confront the model with the experimental data, and then from which we can extract the best fit values from the string, for the string tension, for the endpoint masses, and also for the intercept of the various trajectories. once we have that, that sets up the framework to have a model for the spectra. And the next step is to describe the decay processes. So I mean, 95% of the elementary particles are unstable, and we have to be able to describe the processes under which they decay, the computation of the total widths, and branching ratios. Well, the basic mechanism here will be a simple breaking of a string into two strings, and I'll show you how from that we can compute the total widths and the branching ratios. Now, a special direction will be to analyze glue balls, stringy glue balls. Well, there is some law that one cannot identify glue balls, one cannot disentangle them from flavorless mesons. But I will claim that in the stringy picture one can. So it will be the challenge to see how we identify glue balls. Then I'll describe the issue of scattering. This is something that we did last month. We showed how to connect the stringy Veneziano type amplitudes, the soft amplitudes, into hard one that that is characteristic for partonic scattering. Okay, and then eventually I'll show some predictions about masses and widths of yet unknown states. Okay, are there any questions so far? Okay, so let's go to the first step. So the first step is to define holographic confining background. So everybody here knows what is holography. I don't have to repeat it, but the question is, how do we define a holographic confining background? And what I'm using is the Wilson line, or we may call it Wilson-Malacena line. So we have a description of a stringy description of what corresponds in the boundary field theory to Wilson line. Now, if the string, like in this picture, when the profile is such that there is it flattens, and clearly it will depend, well, when it depends on linearly on the separation distance between the two endpoints, then we say that it associates to a confining boundary field theory, whereas like in the ADS5 process 5, where that is not the case, then the profile is not linear with L, it behaves essentially like 1 over L, then the theory is not confining. Now, what is the precise definition? So if we take a general background where the metric is defined, so these are the space-time coordinate, this is the holographic coordinate, and the transverse directions are all functions only of the holographic direction. Then when we prove some kind of a theorem that sufficient conditions to have this type of confining Wilson-Malacena line is if in two possible cases. The first one is if this G00 times Gxx, if this function, which I call here f squared, if it has a minimum and its value at the minimum is greater than 0. The other one is if this quantity G00 times GUU, if it has a point where it diverges and still this function f at this point is positive, then it is a confining. It will have a linear. We have to recall that these objects are always in holography divergent. One has to normalize it. One normalization way is to subtract this vertical segments, and the renormalized part would be linear with L. And for instance, there are several such background. For instance, the Klebanov-Strasser and Malacena-Nunes, they obey this first condition, whereas the so-called Witten's model obeys the second one. Okay, so let me show you what, just as a prototype, what is the Witten's model. So we have flat 4 dimensions. And then in addition, we have one space dimension. It's a background of a compact D4 brane. So there is an additional space direction, which is compact. And then the space or the manifold of this compact circle and the holographic direction forms a cigar-like shape. And so we have the cigar, the flat, and this part, which is an S4 with a radius which is U-dependent. And you see that if we draw from the boundary, if we take this string, then it will flatten out along this wall. What determines the location of the wall is this parameter in the U lambda in this background. And so this is the prototype of a confining background. Now, the confining background will describe for us just the pure glue theory in the dual boundary theory, and to have also quarks flavor, we have to add we have to flavor branes, D branes, which are representing the flavor, and in the so-called Sakai-Sugimoto model, it's done by adding NF D8 and the NF anti-D8 branes. So these are 9-dimensional objects, but in this cigar they take this U-shaped form, and they can be either antipodally, as in the original Sakai-Sugimoto model, and in what I call the generalized Sakai-Sugimoto, which is very essential for the construction of the HISH model, where there is some separation distance L, and it's not antipodal. Okay, so this is one example. Most of the stuff that I will say from here on is not related to a particular model. It's model independent, but it has the characteristics of this Sakai-Sugimoto within Sakai-Sugimoto model. Okay, so now once we identify this kind of confining background, we would like to look on classical configurations, and we'll have several types of them, and they will correspond to different types of hadrons. I want to emphasize that holography, which is an equivalence between string theory and boundary field theory, practically in most of the application is a duality between bulk fields and operator on the boundary. This is what we get when we take alpha prime to 0, and that is like when we go for closed strings to gravity. But there are quantities like the one that I described before, this Wilson-Valderstena line or Tooth line or Polyakov lines. They cannot be described by fields. For them, we need also in the holographic background strings. And the main point of this model is that, in fact, also the spectra and decay width and scattering amplitude cannot be described by fields. I mean, the most in the most clear way, it's about the spectra. One cannot get a Regge-like behavior from fields. One needs from them for that for this behavior. One needs strings. Okay, so what are the strings that we are talking about? So we start from some one flavor brane, and there is a endpoint of this stringy configuration, and it can end on the same one or a different one. And to get some non-trivial angular momentum, we look for a solution of a rotating string, rotating in a real space. Okay, so for instance, in the generalized Sakai-Sugimoto model, a meson will be of the form of a string connecting the tips of this D8 brane stacks, and so you look for such a solution. The cartoon is that it has this characteristic of two vertical segments and a horizontal one, and it rotates. And these two cigars are in two distinct points in space. Okay, let me give you another example. This will be what we would call a B meson, because it has one end on the flavor brane corresponding to the B flavor, and one to U or D. So this kind of a stringy configuration. And if you solve the Navier-Stokes equation, this is the way that they look like in this particular confining background. Okay, now what about baryon? So since the quark corresponds to the end of the string, then the baryon has to be a structure with NC string connected to something, and this something is what is called baryonic vertex. This concept was initiated by Witten, Gross, and Oguri, and they describe it in holography as taking a wrapped DP brain that wraps a p cycle. Originally, it was a D5 brain wrapping the S5 of the ADS5 plus S5. In Sakai Sugimoto, for instance, it would be D4 brain wrapping the S4 and so on. And now what is crucial is that due to the Raman-Ramon flux, there must be NC strings connected there. So if you look on the Chern-Simon term associated with this flux, then it imposes the necessity of having NC string connecting to this baryonic vertex. So a cartoon will be that we have this wrapped brain. There are NC strings. They could have end on the boundary. That will be an analog of a Wilson line. This will be like the external baryon with infinity heavy quarks, or a dynamical one where they end on the some flavor brain. Now, this kind of the location of the baryonic vertex and the structure of the string is a dynamical issue. You have to solve for the energy of the system and check what is the minimal energy configuration. And a priori, there are many possible layouts we can have. That the baryonic vertex is itself on the flavor brain, and there are NC endpoints that are spread symmetrically, or it can be, for instance, totally asymmetrically, where there is one quark on one end of the string and NC minus one next to the baryonic vertex. And as I said, I mean, it's the dynamics, it's the lowest energy configuration that will be chosen. Are there any questions about it? Just to be sure, do you hear me?
Yes.
Okay. Okay, so I know that I'm okay. Okay, so if there are no questions, I'll continue. And then, well, I'll also come later to describe the blue balls. Now, blue balls are not, they do not incorporate quarks, so it clearly must be closed strings. And in fact, they will be described by rotating folded closed string. I should mention as an anecdote that many years ago, Ori Ganor, Shimon Yankelevich, and myself, we looked on the question of an open string in the case where the target space was two-dimensional. But folded string is, I want to emphasize that it's a very interesting issue that was not discussed very much, and I think that there is a lot to do there. Anyhow, so once we identify this classical configuration in this holographic confining background, we would like to do this map that I told you at the beginning from this higher dimensional curved spacetimes to four-dimensional flat spacetime. So if we look on the solution of the Nambu-Goto equation with these flavor brains, it turns out, for rotating a string, it turns out that it's the same equation as if we take a string, a single string in flat space-time, and there are massive endpoints where the masses correspond to the action along the vertical segment. So if we define the string, this notion of string endpoint mass in the following way, so we take that it is the action along the vertical segment. Then if you place this quantity in the solution for the vertical segments and connect them to the horizontal part, then you will see that the boundary equation of motion, I don't describe the details, but the outcome is that the boundary equation is simply the tension, relativistic tension balancing the centrifugal force. Okay, so that's the picture that we have. Classically, we have rotating strings, and they originally are in this holographic background. We map them into is four-dimensional flat space-time, but the basic idea is that there is a tension which is balanced by the rotation. Of course, when immediately there is a question, what happens when the string does not rotate? What happens when there is no angular momentum? And this is a very important question that I will address later. Okay, so now once you have this configuration, you can also compute the net charges associated with the shift in time of space-time, and in some angle in a plane of rotation, and that will give you the energy and angular momentum. So we get a contribution of the endpoint particles to the energy and to angular momentum, and the contribution of the string. And with the massive endpoints, we cannot eliminate the length and write it as an expression as in the trajectory that relates directly the angular momentum and the mass. But for special cases, when of small masses and large masses, we can. So if we take the case of small massive endpoints, and in particular for the case that beta is close to 1, very relativistic, then the correction to the Regge behavior, so J is alpha prime m squared times 1 minus, this is the correction due to the massive endpoint. So we get a correction that the masses over the total mass to the power of 3/2. And similarly, we can do it for the large masses. Now, when I want to mention that when we do our fit, we do it with the full expression. We don't use this approximation, but just to get the relation, the connection to the Regge behavior, I'm presenting it here. Okay, so that is, again, this is the structure in holography, and it will be a rotating string in ordinary flat space-time. Now, what about the baryons? I mean, we now go from large NC to 3, and we can have this symmetric configuration, which is like a Y shape, or the totally asymmetric one, where there is a string connected connecting a quark and the baryonic vertex to the dipole. This is in holography, and this is in HISH in 4 dimensions. Now, this is just what I said. There is also the possibility to have a delta structure, but I'm now considering the Y shape and the single string between a quark and the baryonic vertex and the diquark. And now it was shown, in fact, also by Truth, that this Y-shaped configuration is unstable. And if an arm is slightly shortened, this will eventually shrink, the arm will shrink to 0 size, and you will get just a single string. Now, we also looked at it, we did some numerical simulation to look for that, and we detected this instability. I want to emphasize that it's not a perturbative instability. Okay, so well, this is just a cartoon of several possibilities, construction of mesons with the charges from -1 to +1, or baryons with charges from -1 to +2, and so these are the diquarks and the baryonic vertex for the baryonic configuration. Okay, so again, are there any questions? Okay, so the next part, which is the most difficult one, is to quantize the system. Now, we know very well how to quantize an ordinary open string in flat space-time, but now, due to this massive endpoint, the string becomes interacting and not free, and there is no way to quantize it exactly. But again, we can do the quantization in the special limits of very small or very large masses. So without masses, going from the classical string to the quantum string, if we are in the critical dimension, this is simply going from the classical Regge behavior to the quantum one, where we add the intercept. Or more generally, if we are not in the ground state, then the nth level will be added to the angular momentum, and this is equal to alpha prime m squared plus a. Okay. Now, what is a? A is what we refer to as the intercept. This is the Casimir energy, or it relates to the Casimir energy. So this quantity a is related to the Casimir energy. It's just A over L, the length of the string, and it's the sum over all the eigenfrequencies of the string. Now, in ordinary string, the eigenfrequencies omega n is n, and therefore we have to sum over n, and we use the zeta function. This is the famous minus 1 over 12, and we get the usual result. Now, in our case, the eigenfrequencies due to the boundary conditions are not anymore omega n equal to n, but they are a solution of this transcendental equation. Tangents omega n is 2q omega n over q squared omega n squared, where q is m, the mass of the endpoint, over Tn. So this is for a simplified case where the two masses are the same, but it's basically that's the structure. And so we have to solve this, which we cannot analytically but numerically, and then sum over all this omega n. Okay, so the form of omega n is quite interesting. Here we start from a very heavy mass, and here is very small one. So we go from, for instance, the level 4 to level 3, C, and so on. So that's the structure of this omega n for the supermassive endpoint. Now, I mentioned before that we cannot use the zeta function regularization for this massive endpoint, sometimes because we get also singularities of the zeta function. And so we had to come up with another idea, and we found that these people, Ambiaz and Sterenko, this is similar analysis, not for rotating string, but for ordinary string. And they said that to calculate this sum over omega n, they will take a function whose zeros are this omega n, and they will calculate this by using the Cauchy integral formula for the case of function that has only simple zeros, no poles, so omega n, that will be the sum of omega n, and it will be just a contour integral over this derivative of the function over f times z. So it has the following structure. We have this the zeros of the function that we want to sum over, and we will do this contour integral along the imaginary axis and along the semicircle. And this is of course already regularized because we took the circle at some radius lambda and not at infinity. So that's the regularized energy when we sum over n, which is a function of the of lambda. And the idea of the renormalization is to subtract from this energy, or to be more precise, we subtract the force. So the force, the derivative of this expression with respect to L for finite L, we subtract from that the same quantity, the force, for an infinitely long string, which is precisely what we do when we analyze the Casimir effect, right? So this is what we use here. For instance, if an ordinary string with no massive endpoint, f of omega is simply a sinus, then it's indeed the sum over n, which is this result in zeta function. But if we do this contour integral, we'll have to do this integral on the imaginary part and this semicircle, and we get that that the result, of course, now with divergent with this lambda, and we go and write down the force. So that will be the force of the string, the Casimir force of a string of length L. For length L goes to infinity, this term will not be there, and when we subtract, this will be dropped, and so we are left over with this, which gives us back the right Casimir energy. Now, this is a very simple function and very simple expression. When we do it with the massive endpoints, it's much more complicated, but we can approximate it again in these small or large masses. So, for instance, for small masses, we get that there are several contributions. If you consider a string that rotates in a plane, then there is the d-3 transverse modes to the plane. There is one planar mode, which all contributes to the intercept. So we get that the total A is this d minus 3 times AT plus A planar. And this is something which is very important, and it deserves a talk by itself. And this is what is called Polchinski-Strominger contribution, or the Liouville contribution. That is what is needed to do to get a vanishing one-loop beta function in the non-critical dimension. And altogether, we get this expression. And by the way, this is exactly this contribution from the Polchinski-Strominger you see in the critical dimension. It will vanish, but we get that instead of having 1, it will be corrected. Well, remember in the 26 dimension, we have 24 trans-resurrection over this 1 over 24, so we get 1, and with the mass it's corrected in this form. And the result is the following. If we present the value of the intercept A, here you see from 0 to 1, and in fact here also with negative values as a function of the beta 1, so the velocity of one of the two masses and the ratio between the two masses. And so you see this black line presents the, this black line presents the border between negative and positive intercept. This is, as you will see in a moment, very important to get negative values. So from the transverse, we can get negative if there is enough asymmetry. For the case where the masses are the same, it's positive. Then we have the planar, and then we have the Polchinski-Strasser, which is always a positive and dominates, and is more important than this other one. And this is the total result. Okay. So we get that. For instance, if we take the case that on one end there is no mass, and the other side there is a mass, then we get from the transverse we get a negative quantity. But if you add to it the Polchinski-Strasser, sorry, this is not Strasser, the Polchinski-Strominger, then we will get a positive. And you will see in a second why it's important, this issue. Okay, so now we ended up this quantization. So in the quantization, I want to emphasize there are two issues. One is that we go from levels which are just level in the integers. We go to energy levels which are different, and the second one is the intercept. These are the two outcomes of the quantization. Okay, so now with that we go to the data, and we
sorry. Can I ask just a quick question?
Yes.
Just the function that you used for this contour integral method was you just subtracted the tangent of omega minus this omega squared divided by omega squared minus 1 that you had.
Yeah, well, yeah. So you see, this was the expression for the energy, and then we took the force and subtracted the force of a string that has the length goes to infinity. What do you do with the Casimir effect? You have two plates, and you subtract the energy of the zero modes of the plate when there is some finite distance between them, and when you take the plates to infinity, right? And that's exactly what we've done here. We subtracted the case of L goes to infinity.
Oh, sorry. No, I think I didn't ask my question properly. I meant the function f on that appears in the contour integral.
Yes.
In this method, that f was
for
this case.
The f is chosen to represent the zeros. For the massless case, this is the f. For the massive one, it's not. It's much more complicated.
So it is not as simply as taking because you had a formula that gave you the omega and implicitly, right?
Well, this was the formula that you have to solve to get the omega n. Okay.
So doesn't it work to just take f of omega equal to that formula, equal to 10?
Yes.
Okay.
So you have to find a formula for f so that it has zeros which coincide with the values of this omega n. Yes. Okay. Any other question?
Can I ask just something real quick? Is that
yes?
Can one use this same method to compute not the value at 0 of the zeta function, but the derivative at 0 of the zeta function?
Well, that's a very interesting question. And in fact, we, with my student Doreen, we did some work to show that there are all kinds of properties of zeta function that you can get by computing it in the two ways, using a normalization of stringy sets up, not the one that I'm describing, using the zeta function and using this other method. And for that, you can get all kinds of properties about the zeta function. I'm not sure whether it can be cooked up for the derivatives, but for certain properties, I can, if you are interested, I can talk to you afterwards about it. There are all kinds of properties of zeta function. Of course, we were, you know, we thought about the zeros of the zeta function, but I don't claim that we can use this to solve Riemann hypothesis, but there are properties of zeta function that you can get from this kind of method.
Okay. Thank you.
You're welcome. Okay, so now let me proceed, and that's in fact a very important and main part, and that's going to extract the best fit parameters. Okay, so you see what we went over quite a lot of trajectories, which means resonances of different values of both J and radial excitation. And so this is J in the plane J n squared, and also n squared or omega n squared. And for various different mesons, and also baryons I'll show in a moment. And the best fits are the following values. So that for the light quark, we get that it's roughly 60 MeV. For the strange, it's of the order of 200 MeV, and for the charm, it's 1500 and then 5 GeV for the B. So this is the values that fit. You will see in a second the trajectories, and also the best fit value of alpha prime is 0.9, and these are the values of the intercept for various trajectories. And I mentioned here also a quantity which is this intercept minus the spin of the particular ground set measure. Now this I'm coming here to what I mentioned before. This is very important. So in nature, if we look on this table that I put here, you see that all the numbers of this quantity A minus S are negative. And it's not a surprise, because the fact that they are negative means that there is a repulsive Casimir force. So what happens is that when the strings are not rotating, then they are not tachyons. They don't collapse to zero size and become tachyons, because there is a repulsive Casimir force. So in general, there are no tachyons in hadrons, both because there are massive endpoints and because there is this repulsive Casimir force. The question, of course, is can we write down the theoretical model, which will include the masses, charges, spins, what have you, and really get to be able to compute these particular numbers. And this is something that we haven't been able to do so far. So as I said, if we do asymmetric masses, we do get negative values of the intercept, but we do not know how to get, for instance, if you take resonances like pi 0, it's clear that it has the same masses on both ends, and therefore we cannot get a negative intercept from that. So this is one of the challenges of this HISH program. Now let me show you some of these trajectories. So for instance, this is a trajectory. So these are the m squared, and this is the J, and this is for omega and eta. So this will be for isospin scale. Okay, so the blue points are the measured quantities, and the lines are the trajectories, and the red stars are, the values of the line at this particular angular momentum. So you see that there is these lines looks like linear. They looks like really the original radial trajectories, but in fact they are not exactly, because we use this massive endpoint, which, as I told you, implies that there are masses of 60 MeV. And the point is that with these masses, we get a better fit than just the linear trajectories. It's not very, very obvious in the hadrons that are built from light quarks. But once we go to a heavier one, so this is for mesons that include strange K and K star. Star is with S equal to 1, and this is the SS bar. You see it starts to bend, and if you go to more heavier ones, like the charmed ones, B and the S, then it's clearly not a linear trajectory anymore. But I think that you see that there is a very nice agreement between the prediction of the HISH model, of the model of the string with massive endpoints, and the experimental data, and it works well with the heavier. It's well, not always such a good agreement, but it's still a nice fit. So this is the CC bar J psi, and this is the big quarks B and also BS, and all of them are work quite well. Now, when we go to the nucleo, the bios, there is a similar nice agreement, but it should be pointed out that for nucleons and for the delta, there is a difference in the intercept between the even and the odd angular momenta. So you see, it's two lines which are separated by some vertical part, which is a difference in the intercept. There are several possible explanations to this difference, which is only when we have this diquark and Biologic Vertex, and there is no such a difference for the meson case. But again, we have nice fits for the baryons made out of light quarks and strange, and this is a doubly strange the cascade, and these are with charm lambda C and cascade C, and you see it's a quite nice agreement between the values of the experimental values and the model. Well, one thing that I want to emphasize is there is a big difference between this hadronic string that I'm describing an ordinary open string. For instance, as I said, I mean, the spin 0 is not a tachyon, but rather a massive scalar meson, like the well, whatever we described there, and similarly, the spin 1 is not you know, a massive gauge field, but rather a massive vector meson. Okay, so next I want to go and consider something which is more complicated and less discussed, and that is the decay. So all of what we have seen in these trajectories are all resonances of decay, and they strongly decay. So it's not, well, apart from these ground set points, where sometimes they do not have a lower state with the same quantum number to decay with, but so they can decay only with weak interaction. But all the others, they are all unstable and they decay. And the question is, how do we describe these decay processes? So the decay in this HISH model, in general in string, is associated with the breaking of a string into two strings. So if we are in type 1, we can have a string that breaks into two strings. So in the worldsheet, this is the form of it. For us, it's that we have this massive endpoint, and when this is created, then there will be a corresponding particular master. Okay, so now the question is, how do I compute what is the probability of such a break, and what is the total decay width for that? Now you would say that it seems that intuitively it should be linear with the length, because the string can break at any point, and indeed this is the case. But the calculation is in fact not trivial at all. So the total decay width is related by the optical theorem to the imaginary part of the self-energy diagram. Okay, so we have the total decay width, and if we compute the imaginary part of the self-energy, then we will get it. Now this is an uninverse diagram in string theory, which is complicated to compute. Polchinski Polchinski et al. Came out with a nice trick to avoid this uninverse by studying a string that wraps the compactify one space coordinate. Okay, And in this case, what they have is it's shown here. We start with a disrupt string, then it opens up, and then it closes again. Okay, so it's we have a closed string, an open string, and again a closed string, which here looks like. So this is a segment. These are the segments which are closed. This and this, and here it's open. This is this part. So if I describe this as a string amplitude, it will be the disk which describe this open sector and two vertex operator, closed string vertex operator. So the whole analysis calculation was transformed into a calculation of the disk with two closed string vertex operators. And our interest is how is this amplitude or the imaginary part of the amplitude, how it's related to the length. And so there are factors that comes from the zero modes, from normalization, and so on. I won't go over the complete calculation, which you also have to regularize. This is the regulator, but it gets some gamma function, and which you, when you take the limit of long string, then we get that it's in fact linear with the total length with the additional corrections. Okay, so our claim is that the decay width, the total decay width of any of these resonances we've seen is linearly proportional to L. L, the length, is the function of the total mass and the masses of the endpoint and the tension. So it has, of course, the dimension of energy. So T times L and some numerical constant. Okay, and for us, it will be the test of this formula. We will take various very different decay processes, and we will check whether this A comes out to be the same in all these cases. Okay, now this is the result for long strings. Once there are short strings, well, then we have to compensate also for phase space factor, which we can write, and we take this into account for these cases. Okay, now so that was for the total width, and also it's not obvious how does this breakup happens in holography. So what happens is that if we have this open string in holography, the two vertical segments and the horizontal one, and it fluctuates, then it cannot break here. But once it hits a flavor branch, then it can end on the flavor. Of course, it's a type 2 A or B, so it cannot have strings ending on points, but on flavor branch it can. So what happens? One has to calculate the probability that this fluctuation will bring this string into one of the flavor branches, and then the probability that it would break. But first of all, the issue is what is the probability to hit this one of the flavor branches? Of course, it has to be a function of these heights, which are the masses, as we've seen before. And in fact, and so we can, for instance, for such a configuration, we have a breaking with a pair of light quark anti-quark or a pair of heavy quark anti-quark. And the result is that it depends on this height z squared over alpha prime, which translates to e to the minus m squared over t. This is if you want, like the Schwinger mechanism, and this was also derived earlier in the context of QCD by Kasher, Nusinov, and Neuberger, and they came out with a formula that it has m squared over t. For them, it was m squared of the constituent quark masses and not the string endpoint masses, but it has the same structure. And I'll show you in a moment the comparison of this result and the previous one for the total width with experimental data. Okay, so for the total width, we take the decay width of states in the row trajectory omega and pi, eta, and so on, and we computed this factor dimensionless quantity A, and you see that it comes out to be roughly 0.1. Here it's with a 10% order, and well, when we go to heavier one, it's 25%, but it's clearly the indication that at least for light quarks, then the decay which is indeed linear proportional, proportional in TL and with a universal constant pi over 2 times A. And this is again for the case of various so omega, pi, eta, k, and so on. It's the decay which is a function of the angular momentum, and there is an agreement. Well, the agreement with the Spectra is better, but it still agrees quite well, apart from several exceptions that we don't know how to explain. But otherwise, there is a nice agreement between the decay widths that are measured and the one that the model predicts. Now, about this ratio, the branching ratio, then if we compare the ratio between decaying into a pair of strange quarks to the one of light quark, then this ratio is roughly 0.3. So we call this quantity lambda s. And when we check several cases, not too many decay into a strange anti-strange, but when several that we were able to extract, like in this case of K3 and K4, then this quantity is indeed of this form. And also when we look on radiative decays, this is also around 0.3. So we have indication that not only the spectra, but also the decay widths fit nicely this stringy picture. Now I want to go over to globals and to exotics. So in the global picture, as we described before, it's simply a folded closed string. For the folded closed string, it looks like two strings. So the tension is twice, and the slope is half, and the intercept is also twice. So this is what distinguishes between a trajectory of mesons and globals. These quantities that the slope is half and the intercept is twice for the globals. Now, what we did, we went over all the flavorless hadrons, the 0++ and the 2++, also 4++, and we try to put them on the trajectories. So this will be trajectories of meson, but there are two points. In this case, it's related to these 2 points, 2 resonances that fit better to be on this vertical, on this slope, which is half the slope. It's just the opposite, but we describe here L squared over as a function of J. But anyhow, we claim that when there will be more states in this region, and unfortunately there are not measured quantities here because they weren't looking at them, and also because they are typically wider and more difficult to detect. But now there is a Panda experiment that hopefully we will be able to see some more states, and then we'll be able to see if there are really several states on these global trajectories in comparison, which are different than the meson trajectories. Okay. Now, I want to emphasize that there are also in this framework that we draw, there are also other type of globals. We can take a baryonic vertex, anti-baryonic vertex, and connect them with NC strings. And in this case, we will get that the mass of the global is proportional to NC, and the slope is proportional, the slope is proportional to 1 over NC. So there are all kinds of lattice simulations where they find globals at various different NCs are roughly the same, small deviations. But if they will find this kind of configuration, then there will be a dramatic difference as a function of n, and you can also draw. So if you, with some imagination, you can also have additional globals from these baryonic vertices and anti-baryonic vertices. Now, it's now very popular to talk about tetraquarks and exotic hadrons. So I want to show you how do they look in holography in HISH. So let me focus on the charm hadron. So If we look on a meson, for instance, CC bar, J psi, it's just a string between this C and C bar. In the holographic side, there is vertical, and horizontal one. And this, for instance, cascade C, it will be a diquark here and a quark, and these are the two C's. Now, in a similar way, you can take now this construction and add to it the mirror of it. So we'll take anti-baryonic vertex and anti-diquark and put them together. And the question is whether this configuration, which will be a two quarks, two anti-quark configuration, is can be detected. Okay, so this is another example where baryonic vertex, anti-baryonic vertex, and now with the C and U, and well, one can play with it, and there are altogether 225 possible tetraquarks, some symmetric, some semi-symmetric, some asymmetric, and the important thing is that since they are based on a single string, then they will have merged trajectories, and then we have spacing that's similar to the one that we have for mesons and baryons, and we can calculate the masses and the width. So there is an example of an object, a resonance called Y4630, which decays predominantly to a baryon antibaryon, which is a very strong indication of the fact that it has, I'll show you in a second, which is it's a genuine tetraquark and not a molecule, and we can compute the masses and the width of the excited states of it. And similarly, one can do the same with and yet unobserved object YB, which will we predict that it will decay to lambda b bar. So in fact, there are two mechanisms of breaking of this tetraquark. The one that I described a moment ago is this breaking. So we start from this system, we break here, and then we get a baryon and antibaryon. So once they identify a decay of an object to baryon antibaryon, then there is a strong indication that it's indeed a tetraquark. But if it's below this threshold, if the mass is below this threshold to decay to this baryon antibaryon, and it can decay to meson to meson, then this decay is done by annihilation of the baryonic vertex, anti-baryonic vertex, and you form these CC bar pairs. And we had a prediction about a CC C bar system, which were observed. So these two peaks were observed, and this one can decay to this cascade CC and cascade CC bar, and this one cannot, and it fits this similar structure. That okay. So Hugo, I mean, how much time do I still have?
So you have 2 minutes, but if you need like a little bit over, that's fine. If you want to go 5 more minutes,
I'll be done in 5 minutes. Okay.
Okay, sounds good.
So before I proceed, are there further questions? Okay, so let me now describe something which is very different to what I discussed so far, but it's very important. The fact that it is important is because this was the reason that string theory were rejected from describing hadron physics in 68. You know, there was this deep inelastic experiment. It was found that the amplitude folds up as a power law, hard and not soft. And if you expand the Veneziano amplitude or Virasoro, you'll find that it has this exponential soft behavior. So since it didn't fit the experiment, then people threw this string theory and they put it aside. And of course, there were two other factors. The one that QCD with a protonic description did have this power law, and on top of that, of course, the fact that string theory was then converted to the theory of quantum gravity and the theory of everything. But now I want to argue, and this is following some work that was done previously by Polchinski and Strasser, and recently we did some more work on that. and that is that using holography, we can bridge between the soft and the hard decays. Okay, so how does it go? The main point, and that's something which is very crucial to understand, is that when you map the 10-dimensional system, in particular 10-dimensional momenta to the 4-dimensional, then there is, if we, for instance, do it in the ATS, there is some warp factor. So if this is the holographic coordinate, then we'll have the 10-dimensional momenta P tilde is related to the 4-dimensional with 1/r. Now, if you, instead of looking on P, you look on alpha prime, you see that it means that, in fact, alpha prime, the slope or the tension are scale dependent. They are different at different holographic scales. And so if you want now to calculate for instance, for closed string, we did it also for open string, the scatter amplitude, then Polchinski and Strassler suggested the following prescription. They said, take the 10-dimensional stringy amplitude that correspond to whatever you want to calculate. For instance, for closed string, this will Shapiro, and then dress it with the weight functions, which are the wave function of the supergravity modes that you are scattering. So if you are scattering a tachyon of closed string, then you take here the supergravity wave function of the corresponding tachyons, and then you integrate over the holographic direction from, for instance, in the ADF hardware model from the wall up to infinity. And when you plug this into here and you use the wave function, then in fact it's a simple calculation to show that using an ordinary wave function, so R0/R to the dimension or to the twist, and if you plug inside the expansion of the soft behavior, this A, but you plug it here, and it becomes S/R squared, and you integrate over R squared, and the result ends up by being a power law behavior. So we went from a stringy to partonic amplitude, and we did this. We derived this amplitude in the hard wall, in the soft wall, and Witten's model. In Witten's model, both in 10 and 11 dimension, we did it for the fixed angle in the Roger limit, and also expanding around the poles, and we get in all these cases not always the same, but it always a power law behavior. So this was for fixed angle in the various models, and then for the pole expansion and for the Roger region. So this is a way to relate this stringy soft scattering to the partonic one. Now I will well, I'll just show that we can use with the trajectories, we can compute also higher states. So for instance, the highest one with in the pi b trajectory is with 4, so we go to 5 and we compute the mass and the width and so on for many other mesons, and also in the radial direction, and also for the baryons, and also in the radial direction. And so let me conclude by just mentioning several open questions. So a question that I mentioned already is the fact that we need to come out with a model that will have negative values of this modified intercept. Maybe this will require some incorporating of fermionic fluctuations. From the point of view of holography, this is not surprising, because everything you start with is a supersymmetric string, but from the point of view of the HISH, and moreover from the point of view of QCD, it's not very natural. So this is a real challenge of how to get this repulsive Casimir process. Now we would like to address strings with charges. People address the case that there are charges, but the charges are opposite sign and cancel each other. That's the way that you get, like in Witten-Seiberg, it's non-commutative geometry. But the cases where the charge, like for the proton charge, is not vanishing, that was not yet analyzed. And also we want to add spins. And in the scattering story, the question is, how do you go from this hartonic behavior to the total total cross-section that is measured, for instance, in this total experiment in LHC. So there is plenty still to work out, but I think that I hope that you were well, you got at least the feeling that this HISH model has a nice agreement with the experimental data. So thank you very much.
Let's thank Kobe. So any questions for Kobe? Kobe, I have a very broad question, which I think is kind of related to, I think, a lot of the interest of people at BCTP. So I feel that, for instance, really the work you're presenting, you're using sort of like the techniques of ADS and of quantum gravity to learn much more about the physics of like mesons, baryons, and like of strongly coupled QFT, right, in 4 dimensions. So, but essentially, like I feel a lot of things that we do seems to be quite of the opposite way, right? So like we use the definitions of field theory to try to learn surprising things about quantum gravity. So I was just curious to ask if during this program, if you found also something interesting from the point of view of field theory that is a surprising thing from the perspective of quantum gravity.
Well, I'll tell you what I did also quite a lot of the stuff that you described in the past.
Of course,
but now I'm in this era that I decided to try and confront whatever we use with experimental data. So you work on large N. Okay, that's very good and very nice, very powerful. Now go and show me what happens when you go back to, for instance, from n equal to 4 to n equal to 0. Show me that you can describe pure field theory using these techniques. And very often people are concentrated in these technical problems that they have, like trying to solve n equal to 4 in the planar limit to any order, to order of 7 loops or 8 loops or whatever. But less emphasis is put in trying to go back and confront it with a global spectra, or I don't know. And similarly in other things, I think I'm not saying that one has to address only Hadron physics, but I want to emphasize that one has to address some physical system. So you want to describe, I don't know, 2 + 1 dimensional condensed matter system. That's fine, yeah. But the goal should be to really describe the properties of this system, and not so much identifying this, I don't know, this higher type of conserved current, this 1 form, 2 form, 3 form, and what so on. I mean, I don't have anything against it, but eventually I want to emphasize this point that, by the way, since you asked this question, starting from next Monday, there will be a program for 2 months in Simon Center in Stony Brook with the title of Large N Holography, Integrability, and Stringy Model Confronting Experimental Data. So I urge you people to attend these talks. If you're not coming in person, then they are all on. They will be broadcast, and one can get them. I'm not sure that people that will lecture there will really put this emphasis, but I'm trying to convince people to also look at the experimental data.
I was gonna say, is it CFT data or is it experimental data? It's like there's a big loop. We got anyhow. Yeah, thank you. Yeah, so if there are no other questions to Kobe, let's thank him again. Thank you very much, Kobe.
Thank you. Okay.